All right, today we are cracking the code on motion itself. Those invisible rules that govern, well, pretty much everything. From a speeding bullet to a falling apple, we're going to see how just a few really elegant principles of physics connect all of it. So yeah, let's dive right in.
What do a speeding bullet, a falling apple, and a game of billiards all have in common? They seem totally unrelated, right? But believe it or not, they all play by the exact same and surprisingly simple set of physical laws. And I promise by the end of this, you're going to see exactly how.
Okay, but before we can really get into the nitty-gritty of motion, we all need to be on the same page. We need to speak the same language. Think about it. Without a universal way to measure things like distance and mass, science would just be total chaos.
And honestly, for a long time, it really was a mess. You had different countries using completely different systems. Just try to imagine building something complex, like a rocket, when your engineer's foot is totally different from your partner's meter. Yeah, that's a recipe for disaster.
So to solve this, the world finally came together and created a truly universal system, the SI units. And what's so incredible about this, what's so elegant, is that with just these 7 base units right here, we now have a common language to measure literally everything. I'm talking from the tiniest atom all the way up to the largest galaxy.
All right, so now that we have our common language down, we can finally start talking about motion itself. And the key, the real metric for understanding all of it, you could even call it the currency of motion, is a single powerful concept: energy.
So, the energy a moving object has is called kinetic energy. And the formula, K equals 1/2 mv squared, it looks pretty simple, right? But that little squared on the velocity, oh, that is so important. It means if you double your speed, you don't just double your energy. Nope, you quadruple it. It's like a massive power-up. Let's actually look at some real-world examples to make this a little more concrete. Do you see a tiny little bullet? Because of its insane speed, it has a surprising amount of energy, 1,000 joules. But then you look at a big, heavy car. Even one that's just crawling along, it packs way more of a punch. And that's all because of its huge mass.
So, okay, we know a moving object has kinetic energy. But what's the next logical question? Well, how do we change it? How do we make something go faster or maybe slow it down? The answer in physics is simple. You have to do work on it.
That's right. You can't just, wish for an object to move faster or for its energy to magically increase. You actually have to do something to it. And that something, in the world of physics, is what we call work.
Now, this is where things get a little tricky, because we all think we know what work means, right? But in physics, the word has a very, very specific definition. You could stand there holding a super heavy box all day long. You're sweating, your muscles are burning, and guess what? According to physics, you've done absolutely zero work on that box. I know, sorry. For work to actually be done, a force has to make something move.
And this brings us to something really neat called the work-energy theorem. It's such a beautifully direct idea. It says that the amount of work you do on an object is exactly equal to the change in its kinetic energy. It's a perfect one-to-one trade, no more, no less. It's that simple.
But what if I told you there's an even deeper rule at play here? What if I told you that in any closed system, energy can't actually be created or destroyed? It can only change its form. This is, without a doubt, one of the most fundamental and profound laws in the entire universe, the conservation of energy. The best way to think about this is like charging a battery. When you lift a ball up off the ground, you're doing work against gravity, right? Well, that energy doesn't just disappear. You're actually storing it in the ball. We call this potential energy. And just like a battery, as soon as you let go, all that stored energy gets released as pure motion.
Okay, let's actually see this in action. Imagine a ball, just sitting right on the edge of a cliff. At this very moment, it's not moving at all, so its kinetic energy is zero. But it is fully charged up, absolutely packed with potential energy, just waiting to be unleashed.
Now, as the ball starts to fall, just watch what happens to the energy. That stored potential energy is being converted, moment by moment, into the energy of motion. That's our kinetic energy. You see, halfway down, it's a perfect 50-50 split. But look at the total. The total amount of energy hasn't changed one bit.
And then, in that final instant right before it hits the ground, bam! All of that potential energy it had at the top has been completely converted into kinetic energy. The ball is now moving at its absolute fastest, but the total energy, it's the exact same as it was when it was just sitting at the top of the cliff. Energy is never, ever lost. It's just transformed. All right, now for the ultimate test of all these principles, a collision. This is where everything we've just talked about, force, energy, conservation, it all comes together in this high-speed, high-stakes game of physics.
Now, to really understand what happens when things smash into each other, we need to bring in one last super important idea: momentum. The easiest way to think of it is as an object's oomph. It's just a combination of its mass and how fast it's going. And here's the kicker. Just like energy, in any collision, momentum is always conserved.
So collisions pretty much come in two main flavors, elastic and inelastic. In a perfect elastic collision, think of two billiard balls just clicking off each other. Everything bounces perfectly. And in that case, both momentum and kinetic energy are conserved. But in an inelastic collision, like a car crash, well, things get bent, they stick together, kinetic energy gets lost as sound and heat. But, and this is the important part, momentum is still conserved.
And this is where you see some really cool stuff happen. In a perfect, head-on elastic collision between two identical balls, the moving one will transfer all of its momentum and energy to the stationary one. It'll just stop dead in its tracks while the second one shoots off. And get this, if they hit at an angle, they'll fly off at a perfect 90-degree angle to each other, every single time. It looks like a magic trick, but it's not. It's just the beautiful, predictable laws of physics at work.
So you see, this stuff isn't just a bunch of boring equations in a textbook. This is the fundamental toolkit that allows us to understand and even predict how our entire universe works. From the orbit of a massive planet all the way down to the collision of the tiniest subatomic particles, these are the rules that run the whole show.
So we've spent this time exploring the rules that govern the world we can see and touch. But what about the invisible world? What happens when we zoom way, way down into the bizarre quantum realm? Do these same neat and tidy rules still apply? Well, that is a fantastic question for another time. Thanks for joining me.